Welcome to lecture 48 of Plant Design and Economics. As of now, we have learned about construction of composite curve. The composite curve can be used to determine the minimum hot utility, minimum cold utility required, as well as the maximum energy that can be recovered between hot streams and cold streams. Now, the composite curve method is a graphical method. In today's lecture, we will learn about an algebraic method, which is called the problem table method. For a given system, the composite curves can be used to determine energy targets at given values of minimum delta T, delta minimum. We have seen that the composite curves are very useful tool for visualizing the heat recovery and the minimum hot utility target as well as minimum cold utility target. This also gives an insight into the problem. However, since this is a graphical method, when you have many streams, several hot stream and several cold streams, the construction of composite curve using a graphical method will be time consuming. Although these days there are several softwares which can be put to use and you actually do not have to take a graph paper and draw the composite curves by hand. Also, when you are using a method that is solely graphical, solely based on graphical techniques, it cannot be very precise compared to an algebraic method. So, algebraic method is generally preferred for the purpose of computation. Here also, for the purpose of computation of utility targets, the pinch temperature, the algorithmic method has been introduced, and we will talk about one method known as the problem table method, which is a numerical method to determine the pinch temperature and the minimum utility requirements, which was introduced by Lenoff and Flower. The use of problem table method will completely eliminate the necessary for using graph papers or sketching of composite curves on a graph paper. So, we have already seen the construction of composite curves. We have seen how these composite curves, in this particular example, the hot composite curve was constructed on the basis of the informations on temperatures and Cp values, heat capacity values, which gives us the enthalpy informations. So, for example, in this interval between T1 to T2, you have only a single hot stream in operation. So, in the composite curve or in the hot composite curve, the contribution comes solely from this stream. So, the H value in this interval in composite curve as well as in this original TH diagram where multiple streams are there are same, and that is T1 minus T2 multiplied by the Cp value of B. But when you come to the next interval, here you see that 3 streams are in service. So, the H value will be T2 minus T3 multiplied by Cp of A plus Cp of B plus Cp of C. You know that the slope of these lines on TH diagram depends on the Cp values, slope equal to reciprocal of Cp. So, here you have a line with different slope on the composite TH diagram. So, this way, on the basis of the temperature and the enthalpy informations, we could construct the composite curves. So, again if you look at this, you will see that these diagrams where we have plotted individual streams and this diagram where I have plotted a composite curve, both the curves are equivalent in terms of temperature and enthalpy. So, if you look at this part and the corresponding part in the composite curve, both have the same enthalpy value and both started and ended between the same initial and final temperature, meaning T1 and T2. So, these H values are same in all these intervals that are shown on the diagram. So, to summarize, during the construction of composite curves, enthalpy balance intervals were set up based on stream's supply temperature and stream's target temperature. We can do the same thing for both hot and cold streams taken together to allow for the maximum possible amount of heat exchange within each interval. So, in the previous case, when during the construction of composite curve, we did separately for hot streams, separately for cold streams. Now, we are saying the same concept can be extended to both hot and cold streams taken together to allow for the maximum possible amount of heat exchange within each temperature interval. However, one modification must be ensured that within any interval hot streams and cold streams temperature must be at least different by the minimum temperature that has been set, that means delta T minimum. So, whatever delta T minimum has been set by you, we must ensure that within any interval hot streams and cold streams temperature must be apart by this delta T minimum that has been set. Now, how to ensure that? Now, this can be ensured if I shift the original temperatures as follows. What we do is, we decrease the hot streams temperature by delta T minimum by 2 and increase the cold streams temperature by delta T minimum by 2. So, thereby we ensure that in any interval always the shifted temperature of the hot stream and the shifted temperature of the cold stream will at least be different by delta T minimum. Note that the shifting the composite curves vertically does not alter the horizontal overlap between the curves. So, when I shift the original temperatures by delta T minimum by 2, either increase it or decrease it, I increase it for cold streams temperature, I decrease it for hot stream temperatures, what I am basically doing is, I am shifting the composite curves vertically. When I shift the composite curves vertically, note that the horizontal overlap between the curves do not change. So, the minimum hot utility target, minimum cold utility target, they do not change. But why do you do this? Because to ensure that the two temperatures are at least apart by delta T minimum to shifted temperatures. So, if the real stream temperatures are used, then some of the heat content would be left out of recovery. This is because delta T minimum requirement. If the shifted temperatures of a cold and hot streams or their parts are the same, then the real temperatures we know that they are still different by delta T minimum, because I have changed them accordingly. So, even if the shifted temperature of cold stream and hot stream are same, we know that they are actually different by delta T minimum that has been set. So, that will allow feasible heat transfer. So, now we will take an example to demonstrate the use of the problem table method, which is a numerical method, and we will go through the algorithm by taking an example. So, we take this example which I have already seen before in our previous lectures. So, I have two streams. Basically, this is the problem where you have two reactors and one separator. So, you have two feed streams to reactors and two product streams from the reactor. So, there are two cold streams, two hot streams. So, reactor 1 feed is cold stream, reactor 2 feed is cold stream, and reactor 1 product stream is hot, and reactor 2 product is another hot stream. So, 2 hot streams, 2 cold streams. So, their supply temperatures, target temperatures are all given, heat capacity flow rates are also given. Now, using composite curve for a target or set delta T minimum equal to 10 degrees Celsius, we see that the hot utility target is 7.5 megawatt and the cold utility target is 10 megawatt. The energy recovery between these two streams is 51.5 megawatt. So, this was already solved using composite curve method. So, we will solve this again using the problem table method, and we must get back the same results. Also note the pinch temperature. This point, so when I say that the delta T minimum is 10 degrees Celsius, that means at this point the vertical distance between the composite curve and the hot composite curve and the cold composite curve is exactly 10 degrees Celsius. So, at this relative position between the cold composite curve and the hot composite curve, the vertical distance between these two composite curves is 10 degrees Celsius. So, we call this pinch. So, there is pinch temperature for the hot stream, pinch temperature for the cold stream. So, they are different by 10 degrees Celsius. So, let us now go through the algorithm. As we discussed that instead of working on absolute temperatures, we will be working with shifted temperatures. So, in the step 1 of the algorithm, we set up shifted temperature intervals from the stream's supply temperature and the stream's target temperatures by subtracting delta T minimum by 2 from the hot streams and adding delta T minimum by 2 to the cold streams. So, this was the given stream supply temperature and target temperature. For example, consider stream number 1, which is a cold stream, which is available at 20 degree Celsius and must be heated up to 180 degree Celsius. So, the shifted temperatures, the shifted supply temperature and the shifted target temperature will be obtained by adding delta T minimum by 2. It is a cold stream. So, the shifted temperature will be obtained by adding delta T minimum by 2. Delta T minimum is 10 degree Celsius that we have said. So, we must add 5 degree Celsius to both this supply temperature and target temperature. So, I obtain 25 degree Celsius and 185 degree Celsius. Similarly, let us consider the stream number 4, which is a hot stream. So, it must be cooled down from 200 degree Celsius to 80 degree Celsius. So, it is a hot stream. So, I must subtract delta T minimum by 2 from both supply and target temperature. So, I obtain 200 minus 5 195 degree Celsius and 80 minus 5 75 degree Celsius. So, this is how I obtain the shifted temperature intervals. So, now temperature intervals are formed by listing all the shifted process stream temperatures in descending order. Also, any duplicate values will be considered just once. So, these are the shifted temperatures that we obtained in previous table. So, we prepare the temperature intervals by listing all these shifted process stream temperatures in the descending order as shown here. And then we prepare the stream population table. So, look at the hot stream temperatures 1, 2, 3, 4. So, this is stream number 1. So, this goes from 25 degree Celsius to 180 degree Celsius. This is a cold stream. So, which is heated up from actual temperature 20 degree Celsius to 180 degree Celsius. So, shifted temperature is 25 degree to 185. Similarly, let us consider stream number 2, which is a hot stream, which is cooled from 250 degree Celsius to 40 degree Celsius. In terms of shifted temperature, from 245 to 35, because you have reduced 5 degree Celsius because it is hot stream. Similarly, another cold stream and the another hot streams are shown. So, we prepare the stream population table. Now, we will perform a heat balance within each shifted interval, and the heat balance can be performed by this equation, which says that you sum up all the heat capacities flow rates for cold stream, then subtract the sum of all heat capacity flow rates for the hot streams, and then multiply that difference by the difference of temperatures in the interval. So, this will give you delta H1, delta H2, delta H3 etcetera for each interval. So, you will look at the interval table and see in each interval how many cold streams are there and how many hot streams are there. You will add up their Cp values and then you can find out this difference and then just multiply by the delta T I values for that interval. So, thereby you can perform the heat balance for the interval. If the cold streams dominate the hot streams in a particular temperature interval, then the interval will be positive, because if this dominates, then the interval delta H value will be positive and we will call that this interval has a net deficit of heat. Similarly, if hot stream dominates over cold streams in a particular interval, then that particular interval's delta H value will be negative and we will say that interval has a net surplus of heat. Now, this notation or convention is consistent with standard thermodynamic convention. For example, for an exothermic reaction, H is negative. Now, once you perform the heat balance according to this scheme, you will see that some intervals will have surplus of heat and some intervals will have deficit of heat. Now, let us understand that heat balance here. So, the entire table is shown now, including the stream population. So, these are the interval temperatures, those shifted temperatures. So, this is the temperature interval, 245 minus 235 is 10, 235 minus 195 is 40, so on and so forth. Now, let us find out this difference. This difference is what? Sum of Cp values for cold stream minus sum of Cp values for hot stream. Look at the first interval between 245 to 235 shifted temperature interval. We have only one hot stream in service with Cp value 0.15. So, this gives us 0 minus 0.15, that is why we have minus 0.15. So, delta H will be this point minus 0.15 multiplied by delta T, which is minus 1.5. According to our convention, we have surplus heat there. Similarly, let us consider next interval where delta T is 40. We have one hot stream, one cold stream in service. So, what will be this value? This will be 0.3 minus 0.15. Cold stream Cp minus hot stream Cp. So, it becomes 0.15 and multiplied by 40, you get delta H for the interval as 6. This is positive. So, following our convention, this has heat deficit. Similarly, when you have several streams, such as in this interval, you have 2 cold streams and 2 hot streams. So, you must find out this difference appropriately. So, thereby Following this, you prepare this entire table and finally, this delta H we see that we get as minus 2.5, that means it has surplus heat. So, this value must agree with the overall heat balance for the data that we were given here. So, find out this sum of these 4 quantities. So, this becomes, if we do this, it becomes 0.5. If we take the difference between these two, it becomes minus 3, but I have 0.5. So, minus 2.5. So, this agrees well with the overall heat balance. Now, the heat balance in each interval ensures the maximum energy recovery within that interval, but heat can also be transferred between the intervals. So, any excess heat available from the hot streams in an interval is hot enough to supply a deficit in the cold streams in the next interval down the line. So, what we can do is we can cascade any surplus heat down the temperature scale from one interval to another. For example, the part of that table is shown here. Let us first assume that no heat is supplied to the first interval from hot utility. The first interval has a surplus of 1.5 megawatt. So, what we will do is we will cascade this to the next interval. But the next interval has a deficit of 6 megawatt. The first one will cascade 1.5, but the next one has deficit of 6, the deficit of 6 megawatt. Now, when this is also cascaded, the heat that leaves after this cascade will have value minus 4.5, because we had 1.5 excess in the first interval and we have deficit in the deficit of 6 in the second interval. In the third interval, which has minus 1 as excess or surplus. So, if we cascade, then the heat that will leave the third interval will have minus 3.5 megawatt. So, this again can be cascaded to the next interval and this will go on. So, this is clearly seen from here. So, we suppose that no heat is supplied to the first interval from the hot utility. So, this interval has excess or surplus heat of 1.5 megawatt, which is cascaded to the next interval. So, the next interval has deficit of 6. So, when this is cascaded, the heat that leaves the second interval is minus 4.5. This is cascaded to the third interval, which has surplus of minus 1. So, the heat when leaves this third interval after being cascaded will have value minus 3.5. Now, this is cascaded to the next interval, which has deficit of 4. So, this when cascaded will have heat value as minus 7.5. Now, this is cascaded to the next interval which has excess of minus 14. So, heat leaving that cascade will now have value plus 6.5 megawatt. The next one will have deficit 2. So, when cascaded, the 6.5 megawatt in the previous interval will go down to 4.5 megawatt. So, this way it will be done down the temperature scale, but now we will see that some heat values are positive, some heat values are negative. Now, heat flows cannot be negative, this is infeasible. So, to make the cascade feasible, what we need to do is we have to ensure that no heat flow is negative. How do I do that? By adding hot utility. So, sufficient heat must be added from hot utility to make the heat flows positive, all the heat flows non-negative at least, greater or equal to 0. So, the minimum amount of heat that is needed from the hot utility should be equal to the largest negative heat flow, because then that value will be 0 and all other values will definitely be greater than 0. So, the largest negative is 7.5 megawatt here. So, what we will do is we will conclude that smallest amount of heat needed from the hot utility is 7.5 megawatt. If I add 7.5 megawatt, what will happen is this value will become 0 and all other will be greater than 0. So, that becomes a feasible cascade. Note that this does not change the heat balance within each interval, but increases all of the heat flows between intervals by 7.5 megawatt, giving one heat flow of just 0 at an interval of this one interval characterized by 145 degrees Celsius. So, this is shown here. So, this was the cascade which is infeasible because some heat flows are negative. Then we looked at the largest negative value and add that quantity to all the heat flow values, and then I obtain this cascade which is now is feasible. So, this value gives me hot utility required 7.5 megawatt and this gives me the value of cold utility that is required. Note that this is the hot utility required and this is going to be the cold utility required. Also, this value gives me the pinch temperature where the heat flow is 0. Note that we could have added more than 7.5 kilowatt or megawatt from the hot utility to the intervals. So, if I add 7.5 megawatt to the first interval, when I added 7.5 megawatt to this first interval, 7.5 megawatt got added to each intervals. Now, I could have added from hot utility more than 7.5 megawatt. That also would have given me a feasible cascade. But since my objective is to find out the minimum hot utility that is required and minimum cold utility that is required, I added only that much to the first interval, which will make that minus 7.5 equal to 0. So, hot utility target becomes 7.5 megawatt and the cold utility target is 10 megawatt. Also, the pinch point or the pinch temperature is indicated by the temperature where the heat value is 0, heat flow is 0. This is 145 degrees Celsius here. So, the hot steam's pinch temperature, the actual hot steam pinch temperature will be 145 degrees Celsius plus 5 degrees Celsius, because I reduce those by 5 delta T minimum by 2, which is 150 degrees Celsius, and the cold steam pinch temperature will be 145 degrees Celsius minus 5 degrees Celsius. So, 140 degrees Celsius. So, hot steam's pinch temperature will be 145 plus 5 degrees Celsius 150, and cold steam's pinch temperature will be 145 minus 5 degrees Celsius, then 140 degrees Celsius. Remember that I reduce the value of hot steams to get the shifted temperature, and I increase the value of cold steam's temperature to get the shifted cold steam temperature. So, that adjustment is again being made, and I obtain hot steam pinch temperature as 150 and cold steam pinch temperature as 140 degrees Celsius. Note that these values agree well with the values that we obtain from the composite curves. Hot utility target 7.5 megawatt, cold utility target 10 megawatt in both the cases, and also the pinch temperature, hot steam pinch temperature and cold steam pinch temperatures. So, both agrees well, and they should agree well. Also, we would like to complete with one comment that the pinch corresponds with either the start of a hot steam or the start of a cold steam. So, if I now look at that steam population table, then the candidate temperatures which can qualify for being pinch temperatures are 245, because it starts 195, because this starts 145, because this hot steam starts here, or 25 degree Celsius, because this hot steam starts here. Note that we have obtained 145 degrees Celsius, which is one of these 4 possibilities. So, we noted that the problem table method is the numerical method which is convenient, and several algorithms or softwares that are available implements this method to obtain the precise value of pinch temperature as well as minimum hot utility target, minimum cold utility target. With this, we stop our discussion here.